Alright, welcome back. Let's keep on trucking. So we stopped on this slide. So let us start. And, well, this is a question for you. It's going to be done in two parts, because first we're going to do something, and then we're going to prove this thing after that. Okay, so here is an argument in English. And it looks a whole lot different than all these symbols that we've been using so far. The first thing that I want you to do is what's called giving the form of this argument. So I want you to translate this English to, like, introduce some propositional variables and make it look something like this with some P's and Q's and things. Okay? When you do that, when you translate English to pure logic like that and give the argument in that way, it's called the form of the argument. So this is translating this to something that looks a bit like this. That's giving the form of an argument. Okay, and one hint is, I don't know why we decided on this, but apparently in English, if means implication from right to left, and the word only if, or the two words only if together, they mean from left to right. So that's why when we say if and only if, we get both. We have decided on these directions, apparently. So use that to your advantage in this example. So take a second to convert this to pure logic to extract the form of this argument. Okay? So assuming that you've gone and done that, let me just confirm I'm still recording, yes. We have to come up with propositional variables for these things. So like, I see three main different things, and I hope you do too. Something about buying a new car, and buying a new house, and getting a job. Those three things, and combinations of them, exist in this entire argument. So these are probably the best things to give propositional variables to. So we'll say, all right, let's say that P is, I will buy a car. Buy a new car. And let's say that Q is, I'll buy a new house. And then finally, let's say that R is, I get a job. Okay, so that's how we can translate those statements to English, or from English to propositions. Not I will get, I get. Present tense. I get a job. Okay, so now it's our job to translate all these lines to pure logic. So I will buy a car and a new house only if I get a job, and apparently only if means from right to left. So it's like all of this together implies that. Okay? So if all these things are true, that means I get a job, apparently. All right. So that is, well, P and Q, right? Given these things we've defined, implies R. That's the one. All right. How about this line? I'm not going to get a job. Sad day. That's not R. Negating it. I will buy a new house. That's just repeating Q verbatim. That's a hypothesis now. And then what we're trying to prove with these things, with those hypotheses, is I will not buy a new car. Okay. Let's see here. That is P, but negated now. All right. So this is the form of the argument right here. This is the form. And now we're going to go and prove it. We're going to prove that it's valid using our rules. So I'm going to copy it and paste it on this nice blank slide that I've made for myself. Boop. So these are our hypotheses, and this is our conclusion. And we have to somehow use these to get at this. All right. So I have a implication and a negation of its conclusion. Do I have anything that I could use with that? Oh, I do. We'll use modus tollens on it to get back the negation of the hypothesis. Here we go. So initially, we have this by assumption. P and Q implies R. That's an assumption, or a hypothesis, you can say. We also have not R. That's a hypothesis. These two mean the same thing. Same reason, just a different word, synonyms. And then now by modus tollens, I have not P and Q. Okay? Because if we have these two things, we can prove not P. All right, and in our case, P was this whole big thing, P and Q. I hope you see that. So modus tollens gives us that, and now it's our job to somehow use this to prove not P. Are you ready? So I don't see anything that looks like this just yet. Not a whole lot of ands in the statement, especially a negated and. So let's simplify this using De Morgan's law. All right, so now I know that because I have this, I must have not P or not Q. It's the same thing. It's De Morgan's law that gives us that. One of his laws, at least. So with this, I know that, and I know Q. I think I can use those to get not P out of the deal. Okay, so now I know Q. That is hypothesis again. So there is a rule that takes these two things and gives us back not P, I believe. Let's find it. Dun dun dun. It appears that I know, let's see here. I know P or Q, and I know not P is true. That means that Q is true. Let's see if we have that. Here's my P, here's my Q. It's really not P and it's not Q. And here is my not P. This is tough because in this case, we're about to use disjunctive syllogism. The P is really not P. The Q is really not Q. Okay, it's the whole thing. And so not P is really not P. Okay? You see that? It's really not P. That is the idea. These are in the wrong order, though, because we know not Q is true. Dun, dun, dun. So we might have to flip it. How about we do that first? Because we do need to use this rule, and we're not quite there, it seems. Because we need it on the left side, apparently. So from there, we know that not Q or not P. It's equivalent. Just some equivalence rule gives us this. It's commutativity of or. Let's say that. Commute dot for or. And then now, by these two hypotheses, or maybe we should be extra precise. This needs a negation, apparently. It needs a negation. It needs a negation of the left-hand side of this or. Let's spell it out, at least this time. We need the negation of this. We actually have it, because not Q is the same as Q, double negation. And so finally these all match up. We got not Q, the negation of that, and that will give us, dun dun dun, that will give us the Q over here. So we have not P, and this is by disjunctive syllogism. So I hope this is fun for you. It is for me. It's just like matching, finding all these patterns. It's like a game. But I can imagine that it might be very, very stressful to try and figure this out the first time. So that's why I'm giving you a ton of examples. And please come yell at me if anything, like in your homework, is not making sense and you don't know like which rules to put where yet. Okay, it is a learned skill. So yeah, we just finally proved what we wanted to prove, and we proved it very, very accurately. In real life, I would probably skip some of these rules. Probably would skip this. It's okay to skip this because it's pretty obvious. Usually. This, sometimes it's okay to skip. If I were doing that, I would say disjunctive syllogism with, like, if I call this 1 and I call this 2, I'd say, like, P equals not P, Q equals not Q. I'd say disjunctive syllogism with these things, so that the reader can still understand, oh, okay, yes, really I need to add a double negation, things like that. It all makes sense. But here I spelled it out completely. And that might be useful for you to do as you're starting out. Okay, so that is inference rules, proving things. The final piece of the puzzle really is how do we prove things when we have quantifiers in our statement? And that's not too bad. It's actually, it involves some surgery, it seems. If you want to prove a quantified statement, oddly enough, you need to remove the quantifiers. You need to get rid of them somehow. Okay, so then you have like the P's and Q's by themselves that you can then go and prove. It's weird to think about, but that's what it takes to prove a quantified statement. We have to be very, very careful because removing quantifiers in the wrong way is incorrect. So you got to do it right. And here's what you can do. So you're going to end up replacing your quantified variables with, depending on the quantifier, either an arbitrary element of your domain or a particular element. Let me say of your domain, just to make it clear. And an arbitrary element has to be like arbitrary. It can't be wearing a certain shirt or anything like that. It has to be nothing special. Any element of the domain should be able to stand for this one arbitrary element. And I'll give an example of that, of course. That might seem very vague and weird. A particular element can be a special element. It can be, okay, 42 is my element, I'm going with that. Whereas that is not an arbitrary element because now 43 does not work in its place. Okay? That is the idea. Let's see here. And one last thing is there's a big difference between proving a quantified statement, like proving something that begins with a there exists or a for all. That's your conclusion. And using one of them like as a hypothesis, like I'm assuming that for all x, p of x is true. Now I can use it to maybe prove something else. Okay, so there's a difference between those things, and I will clear that up right now. So when you're proving something, you have to show that your conclusion is true. Maybe you have multiple and they're ands. But let's just work with one. You have to show that the conclusion is true, but you get to assume that the hypotheses are true. That's how that's the game we've been playing. Like, okay, we're in the truth table column where all the hypotheses are true. We now have to show that the conclusion is true. That is our job when we're proving something. So to prove for all of x, p of x is true, we need to now go and prove p of a for an arbitrary element of a. That's what we do. That's how we get rid of this. We get rid of the quantifier by picking an arbitrary element of our domain and saying, oh, okay, p of a is true for this arbitrary element. A could have been anything. And so that means every element must have worked. Okay? I'm definitely going to give you an example. Don't worry. But that is how you can do it. That's what it means to prove for all. You just get rid of this by picking an arbitrary element and proving that p is true for that element. Okay, that's for all. How about there exists? For there exists, if you have this kind of statement that you're trying to prove, you have to just prove p of b for some element b. You can pick it arbitrarily, maybe everything works, it doesn't matter, or a particular element b. You're allowed to do that here, because you just need to find one good thing, remember. It's up to you. It's not your enemy's job to pick this one. Okay? Or just show that some good element must exist without naming it. That is possible, but very weird to think about, but is the case sometimes. Okay, that's proving. Hopefully it makes sense. I've been talking about it a little bit. We had some hand-wave examples of proving these. To use, like I have a hypothesis, I'm assuming that for all of x, p of x is true. To use this fact, we can extract p of a for any element in the domain. We're like, okay, I know that this is true. I suddenly know that p of a is true. I suddenly know that p of b is true. I suddenly know that p of c is true. And I can use all of these to get at whatever conclusion I'm trying to prove. Okay? Since we're assuming p of x is true for all x, we can, okay, take any element of the domain. We know that p is true. That's what it means for this statement to be true. All right? To use there exists an x, p of x is true, that's a bit weird. It is not very intuitive. The idea is you can extract p of b out of this, but you're not sure which b it is. You just know that you have one thing that p of b is true for. There is some particular element, x, in the domain for which p of x is true, or b such that p of b is true, but we don't know which one it is. Okay? The best we can do is give it a name and say we know p is true for it. That's what we know based on this. There's not enough information otherwise. Okay? So that is the idea. You can either prove or use a quantified statement, and we have some rules now that kind of like formalize these concepts. So here it is. So if we want to use a for all as a hypothesis, we can instantiate it, we say. So if you have some element of your domain that you'd like to use this on, you can immediately extract P of C for that element, because you knew, yeah, it's true for everything. Here's one thing, it must be true for that. That's universal instantiation. That is using a for all in your hypothesis. This one, universal generalization, is proving a for all. It's in your conclusion. So you have to assume that C is arbitrary. You can give it whatever name you want, but assume you have an arbitrary element of your domain, and then you must, for that element, without worrying about too much what it looks like, you have to prove P of C for it. And because it was arbitrary, it could have been anything, so now you know that for all x, P of x is true. Because C could have been whatever, any element you wanted it to be, because it was arbitrary. You picked it arbitrarily. Okay? So don't worry. You'll have plenty of examples of this, if not in these slides, in our proofs chapter slides. We will get there in due time, though. Okay, now let's talk about using, it's here in the hypothesis, using a there exists. If you want to use a there exists, you can break it out. You can break it up into, you know that, okay, I know that there's some element in my domain, call it C. I can pick one out, and I know that P of C is true for it, okay? And there is a caveat here. First of all, you don't know what it is. You don't know which C it is. You just know that there is one. And also, if you use this multiple times, you have to be very careful. Please come to office hours if you'd like a good explanation of why this is true, but I want you to just remember it for the rest of your life. This is one good thing to memorize. If you try to use an existential fact, you always have to define a new element and give it its own unique name. You can't say, okay, I'm going to use this one, call it C, and then, all right, I'm going to use this other one over here, also call it C, and oh yes, they're the same, obviously. No, you can't do that. Okay, it has to have its own unique name. Every time you use an existential variable, it better get a new variable name. C or D, E. Keep going down the alphabet. Okay, so that is how you can use existential variables. It's usually you're not using them, honestly. It's hard to do a whole lot with this fact. Proving existential variables is quite intuitive, I would say. So if you know ahead of time, you have some element in your domain, can be whatever you want, and you know for that element, P of C is true, then immediately you know that there exists an x such that P of x is true. I found one. It's C. P of C is true for that C, so obviously there's one thing in my domain such that P of x is true for it. Okay? That is how you can prove a there exists. All right, so now 2 slides left, and we're out of here. On to the next ones. Let us, together, prove that the following argument is valid, and we'll use every rule, we'll name every rule that we use. Okay, so we have some quantified statements. That's unfortunate, but that's okay. So the first thing that we're going to do, because we're trying to prove a for all, that's our goal, we're going to assume that we have an arbitrary element of our domain. Okay? We say, let x be an arbitrary element of P's domain. If I could only spell. Dun dun dun. Apparently, we know that Q's domain and P's domain are the same. They must be. I promise it's hard to talk and write. There we go. So that's our first thing. And we're eventually going to use, we're eventually going to somehow show that P of our C is true. Or, yeah, let's call it C instead of X. Because why not? Let C be an arbitrary element of P's domain. And eventually we're going to have to somehow get to P of, not X, but C. Okay, and this is more of a straight line proof. I'm going to stop drawing these little arrows for this particular proof to show you what it looks like. I'll use bullets maybe. So we need this because we're working on universal generalization. So this is part of universal generalization. Part of all generalization. Okay, so now we got our C. And now that we have a C, we can use both of these. I hope you see that. No pun intended. Now that we have this and we know we have some element, we can start extracting these P's for those elements. We can use universal instantiation twice. Because I got my C, now I know that Q of C is true, or Q of C or P of C must be true. Because I'm going to use this and C and universal instantiation. Okay, so I know that by universal instantiation, and I also know by the same thing, not Q of C. Okay, because I know for all X, not Q of X. Well, C is one of those. Let's plug it in and get this out. Hey. So again, we have this by universal instantiation. All right. So what do we have next? We need to, now we don't have any quantifiers in these. That's very useful because our end goal is eventually going to be P of C, okay? Because that will give us, at the end of the day, R for all X, P of X. Okay, however shall we do this? So let's look at our rules. So I have an or and then a not of one of those things. Aha, it's my disjunctive syllogism again. So we can use those together to get out, if I know one of the sides is a not, the other side must have been a true. Okay? Dun. So I get P of C out of this because I have a not here and an or here. So this we're assuming is true. We're saying that this side is false, so that means this is the one that must have been true. That's the idea. So this is by disjunctive syllogism, right? Yes, disjunctive syllogism. Weird names. And then finally, because I have 1 and 2, this one we can always assume, I have just proven what I want. Therefore, for all X, P of X by universal instantiation with 1 and 2. No, sorry. By universal generalization with 1 and 2. My bad. We're proving this for all. Dun. All right. So this is how we proved a for all statement. Isn't that fun? So this is essentially what your proof is going to look like. Eventually we'll get to the stage of writing this in English, and it'll look a whole lot less like this. But this is a good place to start, just pushing around variables, because that ingrains these rules in our mind. So yeah, now you know how to prove everything, really. We are ready. So here's an example just for you, and I want you to, again, do 2 things. So first you're going to find the form of this argument. Make your predicates get your hypotheses, figure out what the conclusion is. And then you'll also use your rules of inference to prove that the form is valid. Okay, so take a second, find the form, and assuming you're back with your form, let's talk about things. So this has nothing to do with anything. It's the domain is a set of athletes on the team, so we'll take that and remember it. But here are some things. So we got some practicing hard and some playing badly. Again, we have it. Again, we have it. So it looks like those are our two. They're in fact predicates this time. So let's say P of X is X practices hard, because anybody on the team could either practice hard or play badly, right? It has to be a predicate. It can be true for a particular X, but not another. And then we can say that Q of X or Q of Y, doesn't really matter. They're just variables after all. That Y plays badly. So now, let's create the form of this argument. So the form is going to be, well, this is saying everyone practices hard or plays badly, or both. So this means inclusive or, not exclusive or. So everyone, that should scream for all in your mind. So for all X, because the domain is all athletes, for every athlete, column X, it's true that X practices hard or plays badly. Okay, I hope you see how I'm converting that. Someone does not practice hard. Oh, there exists an X, somebody, such that it's not true that they practice hard. Okay? And then, therefore, someone plays badly. There exists an X such that Q of X. Okay? Someone plays badly. So, here is the form of the argument. I hope you can see it. That is an X right there. Now, we have to prove it. Let's use our rules of inference to prove that this form is a valid argument. All right. So it's valid. That means if these things are true, then this is always true. Doesn't matter what the predicates even meant at the end of the day. So again, let's make me a nice blank slide. And bring over the form. Boop, boop. There we go. So here's what we have. Our hypotheses, our conclusion. Now we have to use our rules to come up with this. Are you ready? So we have to prove an existential. So we have to show that there is one thing such that Q of X is true. There's one X such that Q of X is true. All right, so we need to find some element of our domain, and we can't get one from the for all, because it's like, all right, just plug in anybody, but we can get some element of our domain from this existential quantifier, because we can extract. We can use existential instantiation for once. We can get out of an existential. We have a particular element, and we know P is true for that element. Okay? So, we have, let's see here. C is an athlete, and not P of C is true for C, for that athlete. Okay? And we get both of these from as existential instantiation. These are horrible tongue twisters. Okay. Both of these come from existential instantiation. All right, so I made my C. Now I'm going to use it. All right, and now maybe you can try to do the rest. Eventually, you need to get at exists in X, Q of X. See what you're going to do. What's your game plan? I think, well, if you're going to try and prove there exists, you need to prove P for that thing. And we have a thing. Let's try and use C to prove Q of C, because that will give us there exists an X, Q of X, because C is that X. Okay. Hopefully all of these variable names that I'm saying do make sense as I'm saying them. Okay, so I have my C now. I can plug it into this one to get P of C or Q of C. Because you told me, I'm assuming, this is true for all the x's. Well, it must be true for C, right? We get that by universal instantiation. Okie dokie. And then, what do you know? I got these again. I think you know what's happening. We can immediately go and prove that Q of C is true by disjunctive syllogism. You remember the rule by now. Whee. I was like, all right, well, I know this is true, and I know that this is true, so if P of C is false, and this whole thing is true, that means the Q of C must have been true. That is my proof of disjunctive syllogism, but you can definitely use a truth table to prove it. And so we have Q of C now, which means we just proved there exists an xq of x. It's C. Dun dun dun. It is existential generalization with the fact that we know that C is an element and P of C. One, two, we'll number them. People like to do that in math. Existential generalization with 1 and 2. All right? So we have just proven together a there exists. Excuse me. All right. Hopefully this is not horribly confusing. It is weird to learn this for the first time, I know, and that's why I am giving you example questions that are very similar to your homework problems. Okay? So hopefully with me talking about this, with you reading about it in your book, and with you practicing these some more in your homeworks, it's all going to make sense. But that is all I have for you for this first chapter of your textbook. So we're going to come back and talk about proving things in general. Now that we have a strong foundation of logic, we're going to use logic at a higher level to prove things. It's not going to be in the forefront anymore. It's going to be in the back of our minds. So let me switch to the next set of slides, and we'll continue from there. All right, so in the last 15 minutes or so of this lecture, let's start the next set of slides. It's on proofs themselves. So using all the tools of logic that we've built up together, how do we write a coherent proof that isn't just, okay, I'm using this rule and doing that thing. That's a bit cumbersome. We can do better. All right, so let's get started. Let us prove all the things, and I encourage you to figure out where this proof breaks down. All right, so before we get started, I want to try and trick you into liking math, because maybe you are not a fan, okay? And maybe you chose computer science because you don't want to do any math. So let me try my best here. So learning about proofs and how to prove things is a different kind of math than you might have been exposed to. It's like higher math, advanced mathematics, they say. And this kind of mathematics from here on out, it has absolutely nothing to do with plugging in numbers and computing values, which is maybe something that you've only ever experienced in a math class. Like that's all math has been to you so far in your mathematics career. And it is my job to now tell you that math can be beautiful. Okay, it can be abstract, and you can deal with more pictures than numbers. And in your upper division computer science classes, we're going to be using this kind of math quite a bit. Okay? And in a certain very precise sense, proofs are really programming. And writing proofs is either writing a program or it's something beautiful. It's like art. Okay? So I'm going to show you some extra cool proofs in this set of slides. And I would totally double major in math if I could go back and do it all over again. Okay, that is my rant. I will now proceed. Okay, so we're going to talk about numbers a little bit and prove things about them now. So here are a ton of definitions. Let's go through them one by one so that we understand what they mean, because you've heard all these terms before. Let's just now finally formally define them using logic. That's the entire point of learning logic. Okay? So an integer. An integer is a number that is whole. It's like negative 1, 1, negative 2, 2, and then there's also 0 at the front of all that. Blah, blah, blah. Those are the integers, right? And an integer, we say, is even. Oops. Okay, my tablet is happy again. Sorry about that. So we say that an integer is even if there is some other integer k such that x equals 2 to the k. Like it's exactly a multiple of 2. That's what it means to be even. So it's even if there exists an x such that, if there exists a k such that x equals 2 times k. So that's, in logic, what it means to be even. Similar to even is odd. So an integer is odd if it's exactly 2 times something plus 1. There's a 1 left over. There's a remainder. There exists a k such that x equals 2 to the k plus 1. And I think if you think hard enough, you'll notice that it can't be both of these at the same time. All right. A number is rational if there are integers x and y such that y is not equal to 0 and r is x over y. So it looks like this. There exists an x and there exists a y such that y is not equal to 0 and r is x over y. That's what it means to be a rational number. It is the ratio of two other whole numbers. Okay. An integer x divides an integer y, so it goes cleanly into it if, and only if, x is not 0 and y is equal to kx. So here's the first time it started to say if and only if. Really, when we make definitions, we always technically are saying if and only if, which really means biconditional. Okay, so in math, sometimes you say if when you really mean if and only if, and you kind of have to use your judgment there, which is unfortunate, but that is life. So we say an integer divides another integer if and only if x is not equal to 0 and y is equal to kx for some integer k. All right, so we say that x divides y. It looks like this. We say it like this. X divides y means if and only if there exists an integer k such that y equals k times x. Okay, that's what it means for x to divide y. Okay, so other words for this are y is a multiple of x is a factor of y, x is a divisor of y. Okay, things like that. You may have heard one or more or all of those before. Okay, primality, that's very important. That was the topic of your first lab, right? So an integer is prime if and only if, well, it has to be greater than 1. We're not going to make any negative numbers, or 1, or 0. We're not going to call those prime. And for every positive integer m, if m divides n, then m equals 1 or m equals n. That's trying to say that the only things that can divide a prime number are itself or 1. Okay, let's see here. Dun dun dun. So n is prime. We can write it like this, n prime, if and only if, and now here we get a bit fancy. We say if and only if n is greater than 1 and for every positive integer m, this is how you write this in math, for all m, you can write it in one of two ways. You can say for all m and then say, oh yeah, it's greater than 0. Or you can say for all m just by itself and say that m is greater than 0 implies one of the two. So for all m is greater than 0, it's positive, implies that if it divides n, this gets a bit hairy, unfortunately, m divides n itself implies then m equals either 1 or n. And what I'm trying to say is you don't have to memorize this, just understand how to translate it. A number is composite if and only if for n greater than 1 there is an integer m such that m is between 1 and n. It's not either of them. And m divides n. Okay, so let's try and write this ourselves again. We say n is composite. Again, we don't count anything that is 1 or 0 or a negative number as composite. If and only if n is greater than 1 and there is an integer m such that, I'll write it over here, there exists an m, it's an integer, and m is between 1 and n, and m divides n, just like that. Okay? That's what it means to be composite, and these are two separate things. So we can get logical if we need to. Now we know how, and that's the point. Okay? We break it out only when necessary. Okay, so our first example for this set of slides is, our first problem is, tell me whether n equals 42 is even or odd. I know this, you're probably laughing at this question, but I want you to formally show this. Prove to me, beyond a shadow of a doubt, that n equals 42 is even or odd. You pick one. Okay, if it's even, show that it equals 2k. That's how you prove that. If n is odd, show that it equals 2k plus 1 for some integer k. Okay, so assuming you did that, come back here. I think you remember that 42 is even, so let's prove to each other why. Why in the world is it at all even? So we say n equals 42 is even. This is how we write our proof. Because n equals 2 times 21. Okay? And its evenness now follows from the definition. Okay? That's the idea. So the definition of even is n equals 2 to the k for some k, or 2 times k for some k. Well, here's your k, my dude. It's even. That's how you prove it. Okay? No logic, no like lines of things involved anymore. We've gone beyond that. We don't have to prove existential things. Like, it's suddenly becoming more English. Okay? And we can convert this to logic if we want to, if we have to, if we're asked to on a test. But we don't go straight there. Okay? Also, try something new. Try something with logic and numbers. What does it mean for me to assert that it's not true that x is greater than 42? How would you write this without the not? Take a second to think about that. And assuming you have, okay, how in the world would you do this? Okay, so if it's not true that x is greater than 42, so here is 42, and we're saying that it's not true that x is greater than 42. So here's all the numbers greater than 42, on that way including 42. So we're saying that it's all the ones over here. Yes? So it's all the ones strictly less than 42. Ooh. Or less than or equal to, my bad. Dun dun dun. Strictly greater than 42, not equal to it, my bad. I draw a little dot like that. So it's x less than or equal to 42. Okay, just use the number line. All right, now try B. It's not true that y is less than or equal to negative 100. So that's inclusive. Here's negative 100. And here's everything less than or equal to it. And we're saying that's not true. So it's everything strictly greater than it. You see that? Y greater than negative 100. It's not true. It must be the opposite. That is the opposite. And there's a bit of a pattern going on. You kind of like flip it, add an equal sign, flip it, get rid of the equal sign. And let me show you the full pattern if you've never seen it before. So here's how you negate comparisons. All right? Use those number lines. If you're trying to negate something is less than something, like it's not true that x is less than y, or let's just pick a real number, 42. Draw it. Draw it if you need to. Find 42 on the number line. Okay, it's strictly less than, so it's not including 42. And here's everything strictly less than it. We're saying we want the opposite, so we want everything over here, including 42, because we didn't originally include it. So it's everything greater than or equal to 42. Okay? It's greater than or equal to. And if you play this game for all of these, or at least for all the comparisons. It looks like this. You swap it, add an equal sign. Swap it, get rid of the equal sign. Swap it, get rid of the equal sign. Negating equals, well, what does it mean for x to not be equal to 42? Well, here is x being 42. If we say that's not true, it's got to be everything over here and over here, which is not equal to. Okay, that means x is not equal to 42. That's how you get rid of the negation with numbers. And then this, if you think hard enough about it, it becomes equal. So if it's not true that x is not equal to 42, that means that x is equal to 42 after all. Okay, so that is how you negate comparisons, and it is super fun stuff. All right, so now a few fancy terminologies that we've also seen a little bit already. Let's talk about how to actually go and do a real proof. Okay, so a theorem is a new term. It's a statement that you can prove to be true. It's something that you're asserting. It's something that you want. Like theorem, all pigs fly. I'm about to prove this to you when you say the word theorem. Okay? And to prove a theorem, we have one tool already. We have logic. And you can also use any of the assumptions that you made in the proof statement. You can also use some assumptions that you make outside the proof statement if you do it carefully. Some special kinds of statements that exist outside and are just assumed to be true are called axioms. Like, so it's an axiom that 0 is a number and it exists. That could be taken as an axiom if you wanted to. Those are assumptions that exist outside the proof statement, so not the hypotheses, but still something you assume to be true. You can also use any previously proven statements or theorems, which is really nice because then you can build all of mathematics one by one. And yeah, I said this to you in the last set of slides, but I just want to keep on driving it home. A proof looks like this. It's, okay, assume that my assumptions are true and any of the previously proven theorems are true, and use that to imply the conclusion must be true. So if all these things are true, then the conclusion must be true. And then we know how to use logic to take it from there. But we're going to try and do it in a more Englishy style. Okay? So that is the topic for these slides. And so this is where I want to stop for this week. I'll see it in your lab video, of course, but this is the end of the content, at least for the week. We're going to come back and talk about how to prove for all again from this chapter's point of view. Okay, so I will see you in your lab, and then I will see you right back here on this slide next week.